In this video, we're going to talk about the antiderivatives of exponentials and logs. We just learned the derivatives, and now we can go backwards. Alright, so remember our third major topic of calculus is integrals. We have limits, derivatives, and integrals. Integrals represent the area under a curve, and we figured out that using the fundamental theorem of calculus, we can take an antiderivative and plug in some values to figure out these areas under the curve. So antiderivatives end up being really important when we're trying to talk about integrals. So far we know a few basic antiderivatives rule. We know the reverse power rule, which instead of subtracting one, we add one. So we add one to the exponent and then divide by that new exponent. The antiderivative of sine is negative cosine, because if I take the derivative of negative cosine, I get back to sine. The antiderivative of cosine is sine, because I take the derivative of sine, I get back to cosine. So whenever you're doing these antiderivatives, especially the simple ones, it's always good to check, if I take the derivative of this, do I get back to that? Alright, so whenever we're learning a new integral, we just remember it's the reverse of a derivative. So for exponentials, when I take the derivative, I get the same thing. So when I go backwards, I just go back to the same thing. So exponentials are great. Derivatives and antiderivatives, not too bad. And we learned the derivative of the natural log. It went to 1 over x. So now if we try to go backwards from 1 over x, we get the natural log. Alright, so we're going to find the antiderivative e to the 8x. Alright, these are the ones, whenever there's just a number next to the x, you could go through, alright, it's not just an x in the parentheses, you could go through and make u8x and go through all the process of doing u substitution. But these ones, the AP exam kind of expect to do a little bit quicker, so here's how to do it quicker. We know when we anti-differentiate an exponential, we get back the same thing. But because of this 8, there would be a chain rule when I do the derivative. When I do the chain rule, I'd multiply by 8. So since I'm undoing the chain rule, I'm going to divide by 8. Alright, so this is the antiderivative, because now if I took the derivative of this, when I did the chain rule, this 8 and this 1/8 would cancel and get me back to here. Alright, so this kind of thing, when there's just a number next to x, alright, you can just undo it by dividing that number. Alright, when there's more complicated stuff, you have to do the full u substitution stuff. With these ones, we just want to be able to do quicker, because they come up often, rather than just having e to the x, putting a little number in here makes it a little bit more complicated. I wrote this one, x cubed plus x over x squared. This one looks really complicated. And we learned how to do this type of problem a long time ago. And actually, I think we had one like this in a warm-up, and I realized there's part of it we couldn't do. So let's talk about why. So to do this one, whenever there's a single term in the bottom, it's useful to rewrite this as multiple fractions. Because each of these fractions is going to simplify nicely. So x cubed over x squared just simplifies to x. X over x squared simplifies to 1 over x. And now I can take the antiderivative. X to the first becomes x squared over 2. All right, here was the problem when we tried to do the antiderivative of 1 over x before. 1 over x is x to the negative 1. When I try to take its antiderivative, I would add 1 to the exponent. Negative 1 plus 1 is 0. And divide by the new exponent. But I can't divide by 0, so this didn't make sense. But that's because 1 over x is the only power of x where you actually don't get another power of x. We just learned this. The antiderivative of 1 over x is the natural log of x. Alright, so this really weird thing that like 99 times out of 100 or whatever, when you're dealing with a power of x, you just do this reverse power rule, but only when it's 1 over x do you get the natural log as your answer. And a lot of times you'll see the natural log answer is written with the absolute value, because we can only plug in positive numbers into the natural log. All right, so you'll see this a lot. I wrote the antiderivative of x squared e to the x cubed. Well, here we have something way more complicated than just, in our previous example, we just had 8x. It's pretty simple, it's just a number next to the x. But now we have an exponent, which is way more complicated. So this one we're actually going to have to do u substitution. So u is going to be the thing on the inside, which in this case is x cubed. We take the derivative of this equation, du equals 3x squared, dx, because now we're taking the derivative of x, and then we divide du over 3x squared equals dx. All right, so this allows us to rewrite our problem. All right, x cubed is u, dx is du over 3x squared. You know you've done u substitution correctly when you can cancel out all the x's. All right, this 3 on the bottom is going to stay on the bottom, and also numbers you can just take out there. The antiderivative of e is just e, so the 1/3 is going to hang out. The antiderivative of e to the u is just e to the u. And then we plug back in what we had. And that gives us our final answer. All right, so whenever you have more complicated things than just like x and a number, you can't do that little shortcut that we talked about in the first example. I go through the whole u substitution process. All right, this one, can't do it the way we did our second example. We split it up into 2 fractions because there's this minus sign here. All right, so you can't split up things into fractions unless there's just a single term on the bottom. So you got to figure out some other way to do this. If I'm looking at this, the thing I kind of noticed, if I look at the bottom and the top and I compare them, I notice that the top is exactly the derivative of the bottom. So I'm going to make my u the bottom of this fraction. And this is going to happen a lot now that we have the natural log as an antiderivative. And we'll just see why in a second. All right, so du is 3x squared minus 2 dx. You divide du over 3x squared minus 2 equals dx. All right, so that's rewrite our integral now. We haven't done anything with the top. The whole bottom we called u, and dx is du over 3x squared minus 2. We get lucky. This whole top cancels out with that whole bottom. So we get 1 over u du. And this is the reason why we're going to have to start thinking about when we can't really recognize how to do an antiderivative. What about just making the bottom u? Because if we make the bottom u, we get something 1 over u. And the antiderivative 1 over u is just the natural log of u. And that's the natural log of x cubed minus 2x. And again, we're going to put absolute values around this because we can only plug in positive numbers into the natural log. All right, so because now we can take the antiderivative of just 1 over a value, a lot of times choosing that bottom value to be your u value is going to get you down to a natural log answer for your antiderivative. That's a quick summary. Exponential integers tend to be pretty straightforward because exponentials give you back the same thing. I'd be really careful with logarithm antiderivatives because they look like reverse power rules at the start. It's just 1 over x, like 1 over x squared and 1 over x will look really similar, but you do their antiderivatives vastly different ways. One is the reverse power rule, one is a logarithm. All right, so we're going to, of course, practice this, but just kind of add it to your flashcards. All right, now we have these 2 new antiderivatives for exponentials and logarithms.